Yep. So I'll start away. So hello everyone, this is Andy, and I'm an ESA research fellow at ESTEC here in the Netherlands. So today, what I'm going to talk to you about is solar orbiter coordination with Hinode and Iris. I think there are several goals that I kind of want to achieve, kind of for the community. I think the first one is I understand the community has a lot of people who maybe have no experience with Hinode and Iris. So I kind of want to present these two instruments kind of in a brand new view, in case people have never heard of it, don't really know what they actually do, and present some of the coordination efforts, thermal coordination, a result using these two instruments, and that hopefully can start some of the ideas, some of the perhaps start some of the conversation about having a new coordination with Hinode and Iris. So that's kind of my goal. At the end, I'll show you kind of the inner working of how do we actually coordinate solar orbiter with Hinode Iris, and finally at the end I have a tiny personal note to for I guess for the community to really appreciate the time that Hinode and Iris have put in, and also solar orbiter has put in to make these all everything work together. So without further ado, let's get started. So I thought a fun way to really start this presentation is to present some of the stats that's been done using coordinated observations. So here are stats I pulled from ADS and then kind of beautified them using Gemini, using an AI tool. So on the left-hand side, I have plotted the number of papers that was done in coordination between Iris and solar orbiter, and also Hinode and solar orbiter. So in terms of papers that was being done, I actually don't really like these metrics. I don't think papers mean completely portray the picture of how much effort's been put in, how much science we actually learn. But these are kind of the quick metric for us to understand what's been done. So for Iris and solar orbiter coordination, we actually have 23 papers since the launch of solar orbiter, so it was 2020, so about 6 years' time. For Hinode, we have Hinode and solar orbiter together, we had 21 papers altogether. But on the other hand, if we look at all the instances of a soup that was being run, so whenever a solar orbiter observing plan was being run, so for example, one soup could be run 5 times in one remote sensing window, that will count as 5. We actually ran soups for about 145 to 150 times. And out of these 150, let's say 150 times, 64 of them had a Hinode observing program. So they coordinated at least with Hinode. And this number, to me, it feels very high. It's almost reaching kind of the half, 50% or maybe 40-50% point. But 40-50% is not really the whole picture, because if we remember, solar orbiter kind of orbits around the sun, so it kind of spends half its time behind the sun. So because Hinode and Iris, they are kind of Earth-based assets, they're most useful when solar orbiter is kind of coming around to our Sun-Earth line in remote sensing windows. So we take that into account, the coordination rate is actually really, really high. So it's maybe around 70 to 80% of the soup that was run when solar orbiter was in its remote sensing window have a coordinated observations. So when I was kind of crunching these numbers together, I feel like I did feel like there's a sense of validation of what I was doing is actually quite nice. Is helping the community to build up these really nice data sets. And what I think I really want to bring out is intrinsically what this means is that solar orbiter, Hinode, and Iris, they're really painting this complementary picture together. So Hinode and Iris, they're really helping solar orbiter to achieve some of his science goal. But before we dive into kind of what are the science goal that has achieved, I think we want to dial back a tiny bit to understand kind of what are the two instruments, what's on board of, for example, Hinode and Iris, for us to give us a full sense of what's being offered on these instruments that complement our solar orbiter. So kind of kickstart this, I thought I'll start with Hinode, which is also called Solar B. So Solar B was launched in 2006 as these remote sensing spacecraft that's hosting 3 instruments by JAXA, also in collaboration with NASA and ESA. So what I think really fun about Hinode or Solar B is that it's kind of a Japanese tradition. When they launch a mission, they would just call it, for example, Solar A and Solar B, and 2028 we have Solar C. So when it was first launched, it was called Solar B, and after it's being launched, normally these missions get renamed. For example, Solar A was being renamed as Yoko, and Solar B was being renamed as Hinode. And Hinode in Japanese actually means sunrise. So personally, there's like a quirky side of me think it's quite funny to have the sunrise balloon at the same time as the sunrise spacecraft observing the sun at the same time. So when Hinode was launched, it was launched into this sun synchronous orbit. Basically, what that means is that it orbits around the North Pole and South Pole, kind of perpendicular to the Sun-Earth line. So what this means is that it provides kind of this like continuous monitoring of the sun, basically for all the seasons, except for maybe a couple months that where we have kind of eclipse season where some of the viewing is being limited. But most of the time, it will observe the sun all the time because it's through this like North Pole, South Pole orbit. And on board of Hinode, we have three instruments. We have SOT, ICE, and XRT. And these can really be understood by the plots on the left-hand side, where the plot on the left-hand side, I've kind of plotted the solar atmospheric layers. Bottom, we have photosphere, chromosphere transition region, and the corona. So SOT really slots in these photospheric observations were indicated by the blue bar. Whereas the rest of the two instruments, ICE and XRT, they kind of image the corona in extreme ultraviolet and also X-ray. And now we kind of have basic knowledge about about Hinode, about solar B, kind of background knowledge. We can dive a tiny bit deeper into what each of the instruments really does. So let's kickstart with SOT, which stands for Solar Optical Telescope. So SOT kind of images this photospheric magnetic field. What's really unique, which I'm not really sure if it really shows well in this presentation, is that if we look at the right-hand side, on the top row, we have Hinode, and the second row, we have SDO, a HMI magnetogram. And we can clearly see that SOT can kind of help us to image this really spine-scale magnetic structure in the photosphere, using kind of the Stokes profile to derive vector magnetic field. I think not only is vector magnetic field, they also have different observing mode, including like calcium-2H, like a lot of the photospheric line, in a really fine scale 0.2 arcsecond resolution, imaging a lot of the photospheric line. And I think at that time, one of the significant findings was finding like these alpha wave kind of being implied by the calcium-2H line. And here I want to present some of the synergies that Solar Orbiter have been working with SOT to create. So on the left-hand side, again, we have these SOT, really high quality, very detailed magnetogram. And using magnetogram, this team by Maria Tal, published in 2025, using these really fine-scale SOT vector magnetogram, they paired it with kind of a force-free field extrapolation to kind of extrapolate the very tiny small-scale magnetic structure within the quiet sun. And what they were trying to achieve is trying to understand one of the kind of phenomenon that Solar Orbiter has been observing, which is campfires, which is these like really tiny small scale reconnections that's happening kind of ubiquitously in quiet sun. So with the extrapolation, we can clearly see that we see this like tiny little reconnection, tiny little twisted magnetic flux rope in quiet sun that could maybe imply that could form campfires that we see in Solar Orbiter. So quickly to go to the next instrument, we have XRT. So XRT, we're jumping instantly from photospheric magnetic field all the way to corona. So XRT, as the name suggests, is an X-ray telescope. But what I find quite interesting is that especially in the modern view, where we're used to RESI or maybe STIX images, where images are done by kind of deducing the images, or like done by this like moire pattern, where you kind of see these elliptical sources. XRT does this really differently. So how XRT does it is that it has various filter, including like aluminum, titanium filter, in kind of thin, kind of medium thickness and really thick material in front of the CCD. So when an electron hits, by adjusting kind of filter material, filter thickness, we can then, the electron would then hit the CCD and create basically an image using that. So on the right-hand side, let's see if this movie plays. We can clearly see that XRT works very differently compared to, for example, RESI and STIX, where we can see that there are a lot of fine-scale structures that we can see, including the, let me see if I can move this. Oh no. I think including coronal hole, what this really samples is kind of a soft X-ray, maybe 1 megakelvin, kind of maybe bottom of the corona, all the way till 30 megakelvin, which is like flare plasma. And not only in the coronal hole, I think one of the really nice things to be seen by, or can be seen by XRT, is this study by Lucy Green in 2011. At the top, it really shows kind of the strength of XRT, really to like try to image these high temperature plasma that's emitting. For example, at the top row, I've showed these images of a flux robe where XRT is able to image at that time to show there's really high temperature structures within the flux robe. And not only kind of the studies that was done in 2011, we also have a lot of coordinated studies using XRT and solar orbiter together. And below, I've indicated one of the really interesting study that has been done with XRT and STIX together. So from left to right, we have the location of XRT, which is basically at Earth, and we have solar orbiter basically involving this like 90 degrees unique vantage point angle to observe the sun together in this like kind of right angle configuration. And what it did at that time, it was using both of these instruments to observe M3.9 flare using a coordinated observations between XRT and STIX. And on the right-hand side, we can clearly see the STIX view where the red circle elliptical source indicates kind of soft X-ray, and the blue source indicates a hard X-ray of this flare. And this clearly forms like we kind of see this like classical or structure that we're very used to, where the loop top is clearly seen as a soft X-ray source, kind of a thermal source, and we have hard X-ray source kind of at the foot point. And XRT, we can clearly see kind of a very similar picture, except at a very different angle, where you see these soft X-ray signatures at kind of the loop top source. And by having these unique vantage points of 90 degrees separation, what they did at that time was reconstruct this flare using this stereoscopic view to have this like to investigate kind of the 3D evolution of a solar flare thermal X-ray loop top source, which I find very interesting. So if we focus on the left-hand side, these are the 3D loop top sources being plotted on top of J-Helio viewer. So we can clearly see that at the bottom, again, we have these like blue hue indicating the hard X-ray sources observed by STIX. And at the top, we can see this elliptical source that's really interesting. It's kind of the first time we were able to do this kind of 3D reconstruction of a loop top source for the first time, just by combining these two unique instruments together. And finally, I think the thing I want to present is the instruments that I guess I'm most used to, which is extreme ultraviolet imaging spectrometer. So ICE is a UV spectrometer which image the solar corona in maybe a 0.5 megakelvin to about 20 megakelvin range. I think for those of you who don't really, I'm not sure if in the audience, for those of you who maybe have no experience with the spectrometers work slightly differently to our broadband imager, for example, SDO AIA. I normally like to think of SDO AIA as kind of a camera or eye that doesn't separate wavelength from wavelength. We just kind of look at at one broadband wavelength all at once, combined all together. But then the unique point about Hinode ICE is that it has really fine-scale spectral resolution. So if you focus on the plots on the left-hand side, kind of the bottom left plot, we can see kind of the wavelength coverage of Hinode ICE. And within this wavelength coverage, we can see this tiny scale Gaussian shape emission lines across this wavelength. And what this indicates to us is that Hinode ICE is really able to pick out these individual emission lines emitted by, for example, iron 8, iron 9, iron 10, all the way till iron 24 to sample the really hot line. And you can see with the zoom in view on the right-hand side, it really forms this like nice Gaussian shape, where by fitting a Gaussians, we're able to start getting some information that broadband images can't give us. For example, we have Doppler shift indicated by the peak shifting left or right, or blue shifted or red shifted, or we can even measure something called a non-thermal width, which is kind of the broadening of the weird broadening of the lines that we don't really completely understand what happened. And I think one of the really iconic study, or really one of the study that illustrates this powerful spectroscopic technique, is kind of the plot at the top, where I've plotted the study by Peter Yang in 2015 of a coronal bright point. So from left to right, we have AIA 193, which images the coronal bright point. We can clearly see this bright structure at the top. At the center, we have iron 12 195 intensity, So 195 is very, very close to the formation for temperature of 193. So they roughly look at the same structure together. And we can see that if we squint, I think if we squint enough, they basically look the same, except the color table. But I think what's really powerful is that on the very, very right-hand side, we have the iron 12195 Doppler velocity map. And this clearly paints a very, very different picture. For example, if we look at the south of this coronal bright point, we see this big blob of blue patches indicating that plasma is flowing into our line of sight. So flowing basically has this blue shifted component to us. However, because the density or the emission measure of this plasma is just not enough for us to be seen in, for example, intensity map and 193 maps. And there was and the only way for us to image these kind of outflow regions or outflow jet is through the spectroscopic technique. And not only this, not only illustrating kind of the unique points about spectroscopy being able to pull out the Doppler velocity, I also wanted to point out some of the coordinated observations. For example, on the screen here, I have a coordinated observation done by Deb Baker in 2022. So we focus on the very, very beautiful kind of blue maps. These are intensity maps. So it's kind of similar to AIA maps, but it sweeps across increasing temperature. So from the left-hand side, we have maybe about 0.7 megakelvin all the way till like 3 megakelvin. And what we can clearly see is that structure changes. As you go to higher temperatures, structure changes from not having kind of these two structures that form a corridor at the middle to at maybe 1.5 megakelvin, we start to see this two outflow structure with this clear corridor that is pointing to kind of the top left of the plot. And if we look at the Doppler velocity map, this also shows kind of a striking feature where along this corridor, along with this like dark stripe, we can clearly see a Doppler shifted, blue shifted plasma, so indicating to us that plasma is constantly flowing out in this blue corridor. And we pair this with PFSS, so potential field source surface extrapolation. What we saw is that these long corridor corresponds to this really, really long loop that potentially connects to our in situ measurements. And by pairing in situ measurements with, for example, electron density measured using Hinode eyes with the in situ measurements done by SWA and MAC data, and this study really showcased that these long corridor can be the source of slow solar wind. And this kind of suggested that it's through these interchangeable reconnections in this really, really long corridor that create the slow solar wind. And this really, I think I really like this study is because it really tries to answer some of the solar orbiter goal, which is what drives the solar wind and where this wind is coming from. So now we have kind of a brief understanding of what a spectrometer is. And finally, we can go to our final instrument, which is IRIS in this talk. So IRIS was launched in 2013. It's again launched in this sun-synchronous orbit, basically orbit around the North and South Pole. Regarding wavelength ranges, we can clearly see that it's very, very different from Hinode eyes, where Hinode eyes cover about 150 angstrom to maybe 250 angstrom. Whereas in IRIS, we are covering from 1,300 angstrom all the way to 2,800 angstrom. So what this indicates to us is that instead of looking at the corona, we're actually looking at lower down at the transition region or the chromosphere. And how IRIS observed can really be represented by this movie on the right-hand side, where in the background here, we have the AIA 171 image. Let me quickly play this movie. And we can see this very kind of small field of view. It's not very small, it's 120 arcsecond wide field of view being shifted left to right. And these are what we call slit jaw images from IRIS. And these provide really, really fine scale or high resolution images of about 0.33 arcsecond. But not only these like really fine scale, high cadence, as fast as one second cadence observations, we can clearly see that at the middle of these slit jaw images, so at the middle of these small field of view, we have this like dark line at the middle. And this indicates that, and this location actually indicates where we have spectral data with IRIS. So similar to Hinode eyes, we also have spectral data with IRIS as well. So you can clearly see that this image of flare, very nice. We can see kind of the loop foot point source, and we have spectral data along that vertical slit. And when we pair Hinode ice and iris together, I think what we can start to see is they're kind of similar, but they are very, very different in a lot of senses. For example, again, focus on the stratification of the solar atmosphere. Ice covers kind of the corona from 0.8 0.5 megakelvin all the way till maybe 20 megakelvin. But iris samples a lower temperature at about maybe the chromosphere all the way to the transition region. It also has one line in the corona, but I'm not plotting it here. But if we look at the plots on the right-hand side, these plots kind of spectra, so it's kind of the raw data that we get from Hinode ice and iris. If we look at the top again, we see this clear Gaussian shape that is very, very commonly seen with Hinode ice spectra, indicating kind of the optically thin data that we normally observe with Hinode ice. When we look at the bottom, these maps kind of the window of the magnesium 2 H and K line. We can see that although we can kind of, if we squint enough again, we can kind of see this Gaussian shape again. But if we sweep across, for example, the magnesium 2K line, so on the left-hand side line, we can see that it doesn't only form a Gaussian, but it goes up and it goes through this what we call a central reversal at the middle, and then it goes back up again in a non-symmetrical form, and then it goes back down. And what this indicates to us is this intrinsic process that's happening in the chromosphere that indicates to us that not only there's emission, there's also absorption within the line. So by sampling this like magnesium 2K line from left to right, we're kind of sampling different physics across the chromosphere. So instead of having a lot of lines that we can sample across a wide range of temperature, what iris is really, really good at doing is to use one or a few of these lines to really understand kind of stratification or what's happening in the chromosphere. And I think this really, really can be shown here, where this is one of the studies that I really like. Again, if you can focus on the second, kind of the third row, here I again have the magnesium 2K line, which is exactly the same as the previous slide. But not only we have the magnesium 2K line, we have maybe the carbon 2 line, which we see the central reversal again. And by using all these central reversal and all these like left-hand side peak and right-hand side peak, we can kind of do what we call a chromospheric inversion. So we can alter the chromospheric parameters, including temperature, electron density, microturbulence, line of sight velocity, to try to recreate these lines in order for us to understand how the chromosphere being stratified when iris was observing. Of course, one of the strength of iris is not only on its chromospheric ability. The other strength really sits on its high cadence ability and really fine scale, really detailed look into the solar atmosphere. For example, here on the screen here, I've listed again another coordinated observations done by Ryan French in 2024. If we focus on the plot on the left-hand side, we can clearly see that solar orbit and iris, they are at different places, where solar orbit is kind of at the back of the sun, but Earth is, I guess iris is just at the Earth point. But then what was really lucky is that the flare happened kind of at the middle between the two instruments. And what this allowed us to do is for solar orbit to observe this flare and also iris to observe the same M8.6 class flare all together. And what was found in this study was that using STIX and iris, iron-21 line, which is one of the very, very hot line, about 15 megakelvin, it was trying to understand kind of a light curve evolution and also the iron-21 intensity, Doppler velocity, non-thermal velocity evolution. And they clearly see that at the loop top, what they call a loop top or fan structure, they can clearly see this periodic pulsation. So there's a reason why I call them periodic pulsation, because in their study, they didn't even find kind of slowdown of this trend. They're just like they're pulsating for a long time, for about 35 minutes at exactly the same period. So what this indicates to us is suggesting that these oscillations, what we normally call QPPs, they're probably due to magnetic tuning fork in the flare. So again, this is one of the studies that hopefully inspires some of the some of you on what your next observation or next soup could do. So just now, I presented kind of very rough or very fast, brief summary of what Iris and Hinode are capable of. And now I want to get on to what are the inner workings of coordinating observations between Iris, Hinode, Iris, Hinode, and Solar Orbiter. So I've plotted a rough timeline on the left-hand side. If we just focus from the top to bottom, first we have the Solar Orbiter Working Group kickoff meeting, where the kickoff meeting is kind of discussing what soup will be run in the next remote sensing windows. And then after the kickoff meeting, normally what you'll receive is a coordination invitation email from me. What this email details is us inviting you to start thinking about, for your soup, whether you need coordinator observations, what kind of strategy you want, maybe start the community thinking or discussing about what kind of data or what kind of perfect data set they want. After this email, we step into SOWG, where things are a bit more finalized. And then after SOWG, you will again receive another email, which I believe some of you in the audience have received, is detailing some of the observing, kind of how do you organize coordinated observations using Hinode and Iris. So for Hinode here, what we normally do is submit what we call a hop to the Hinode team, detailing, for example, your scientific goal, what kind of observations you want. Do you want eyes, SOT, and XRT together, or do you only want one observation? And really writing who are the points of contact for you to really try to achieve your science goal. And for Iris, what we normally do is we have an Iris request email to really try to discuss with the Iris team. What I really want to emphasize here is that these are really experts who has worked with these instruments for years, or maybe at least like 13 or 14 years. So they really know their instruments and know their limitation of the instruments. So you can really try to discuss with them what is your science goal and try to achieve the most out of your observation. And of course, all these come with a deadline. And after the deadline, Hinode internally, they will discuss all the submitted hops, so submitted observations, and they will start approving them, looking through them, and approve them. I think so far, as long as you wrote a scientific goal, I think the approval rate is about 100%. So as long as you have a reason to observe, normally Hinode and Iris, they're both extremely supportive on everyone's observation. So after the discussion, approval, these hops will be published onto a website on the right-hand side, where you can clearly see that these hops are associated with the name of soup. For example, we have soup major flare watch or soup RS burst, for example. And you also receive an email of your soup getting approved. If there are any questions at the middle, then you also receive all the questions at the same time. And on the Iris side, they will also add these observations to plan, because you will have discussed with the Iris request email before already. So they add these observations in a huge CSV for the coordination to go smoothly. And then throughout this meantime, the external coordination webpage that kind of I'm responsible for will get updated. So this provides kind of a centralized place for all the information to be together. So at that time, when Iris Planner or XRT or SOT Planner go on that website, they will know that for this soup, for this date, you have a coordinated observations. And finally, right before your soup is actually run or your observations actually being taken, we'll have a pointing decision meeting where you start to decide where on the sun you want to point at. And roughly at this time, Hinode will also announce their observing plan through an email. Iris will also do the same about their observing timeline to indicate that your soup will be run on this day, what is the mode being run, how many times will being run, and kind of the telemetry, kind of the detail working of the plan that will be run. So I hope that wasn't a very rush. I hope that was kind of understandable, kind of what the inner working of everything is. And as a final note, I thought a nice way to kind of stop or finish this presentation is to kind of present my personal experience as the Iris Planner, because I've been through this process from coordinating observations to actually putting observations onto the Iris spacecraft. And what I really want to convey is how much time and dedication, I guess, the whole community has put in together for everything to work. So as Iris Planner, normally you will receive this like 35 pages Iris Planner notes where you're expected to read before your first, I guess, Iris planning job. And before every single upload, so we basically have an upload every day. Before every single upload, you have to go through these like 3 pages checklist basically to go through, oh, if I've done everything correctly, if I applied the role correctly, if you checked previous day data, if there's any error. So you can clearly see that there's a lot of work that's being put in. And of course, the checklist is not everything. When we put in the actual observations, we have to care about some of the details. For example, when we look at the active region, normally we want to put on the auto exposure control on, so in case a flare happens, it doesn't completely saturate our detection. So there's a lot of like these like little knots that can be put in. And of course, the software is not written by someone now. It was written probably in 10, 15 years ago. So when you put in observations, normally it will say, oh, the time is not correct, or you happen to be at an eclipse season, then you have to put in observations manually one by one. So I think what I wanted to convey is that this, for the Iris Planet, there's a lot of work. For example, when I was coordinating with Solar Orbiter, I would maybe go into office at 9, and those 2 days I finished at 10 just because of complexity of 10 p.m. just because of the complexity of everything done together. And just credits to Milan. Milan actually gave me some statistics. Overall, we've done 58 coordination week between Iris and Solar Orbiter. We are involving 35 different planners. So planners that are, for example, like me, who are early career researchers, dedicated their 1 week or 2 weeks of time from 9 to 10, or maybe when they're more efficient, maybe 9 to 7, to help the community to build this perfect data set together. We've coordinated with 24 different soups, that's not including cross calibrations, and all the EUI observations would have coordination. And of course, this is only the side about Iris. Here they would have done exactly the same thing. So what I want to convey is not to us. I don't want to convey a sense that this is a difficult task, but I just want to convey that there's this. I hope there's a sense of appreciation that everyone did their job in order for us to get this perfect coordinated observations, for us to create all these papers and scientific output together. As the final slide, I hope Milan doesn't mind, but when I asked Milan for the stats, this is kind of the footnote he attached. So I think it's quite a nice way to stop this presentation on coordinating with Iris and Hinode, and kind of represent a general view of Hinode and Iris. Is that for all of you who are interested in Iris, maybe inspired by this talk, or interested in Hinode observation, please feel free to contact me, any of the instrument team, and we'll all do our best to assist you with the data or analysis. So that's kind of the end of my presentation. Thank you. I hope it was interesting.